Hello, class. Thanks for joining me again for 9-4. We're going to look at part 2 here, but we're actually going to focus on a new theorem, but let's just kind of reiterate what our previous theorem said. All it said was if you created a triangle, okay, in this case it was A to C to D, and you created a line somewhere in the triangle where it touches two sides, and then in this case it was BE, and that side happened to be parallel with one of the other sides, BE and CD are now parallel, you end up creating proportional parts in the sense that AB is now proportional to BC in the same way, or it creates a ratio that is proportional to the same ratio that AE makes with ED. Now, you have a new theorem up here in the upper corner that you can kind of write down, but it's pretty simple. We have this triangle ABC, and you have this line segment ED. Now, it says that these two lines are actually proportional to each other. Or, not proportional. They're actually parallel to each other. But the truth is, by the way this theorem is written, it should be written as this triangle has this line segment ED, and we don't know if it's actually parallel yet. But all it says is if you actually compare the ratios of, let's say, AE to EB, and then you compare the ratio between these two sides to the ratio of CD to DB and the ratio of these two sides. If the ratios are proportional or equal to each other, then you know that these two lines are parallel. So the logic's actually just kind of backwards, and it's not too bad. Okay, so let's go ahead and work on a problem that actually might exemplify that. So let's take a look at this here. This one seems easy, but it can be very, very tricky. So let's see. So go ahead and draw this on your paper here. You have this triangle DEF, that's the larger triangle, and you have this line segment GH, and we don't know yet if GH is actually parallel to DE. That's the final question here. Is DE parallel to GH? So in this case, we know that EH, the given information says that GEH is 3 and HF is 9, okay? And all we're given here is that DG is 1/3 the length of GF. I think you can already intuitively tell that there's something going on here, and I think that GH is going to have to be parallel to DE. It just seems right, because you're hearing something about 1/3, and then you got 3/9 here, and that looks like it's 1/3, like 3 is 1/3 of 9. But it's just, how do you set up the math here to make sure you could justify that everything is true? These two make a ratio that is the same as this ratio here. So the first thing that we're trying to prove is that, first, write out the ratios that we want. We want our ratio to be EH. Who do we compare EH to? Well, it's going to be to HF, because supposedly if these two lines were parallel, right, DE and GH, then it should cut EH and HF. It should cut these two parts to creating some kind of ratio that's proportional to how these two parts now are going to create a ratio that's proportional to the ratio of these guys. So let's see. EH to HF should be proportional or equal to the same thing, or the ratio that DG and GF makes. DG over GF, right? Now, we have no problems with saying that EH and HF are 3/9. That looks about good, but we don't know how to set this up. This is kind of odd. All we're given is that DG is 1/3 the length of GF. Well, if you don't know where to begin, because you don't know what numbers you're supposed to plug in, let's just talk about it in terms of X. Why don't we just say that DG is some length that we don't know, right? It's literally X. It's some value that we just don't know. If you think about it, GF, it says here that DG is 1/3 the length of GF. So what does that mean in terms of X? If DG was X, that would have to mean that GF is 3 times bigger than DG. And if you think about this, X divided by 3X, that's like looking at, if you can look at it, the units of, or the variables X and X cancel out to 1, you end up actually getting a ratio of 1 to third, or 1 over 3, which makes sense. dg is 1/3 the length of gf. So sorry to kind of confuse you there and make a little side note, but that's what I got so far. And you could have set it up like this too. Some other people do this, but I think it makes it a little bit tougher. Some people say that they like to start backwards. They like to say that gf has a length of x, and then dg is 1/3 that length. These two things you can use. It does not matter which one you decide to use. But I don't like dealing with fractions. So if you can see here, dg is 1/3 the length of gf, which is 3x. Here you can kind of look at it the same way. If gf was an x, then again dg is 1/3 the length of gf, according to what this problem gave us, or what this problem presented us in the information. dg is 1/3 the length of gf. Okay, so you can plug in whatever numbers you want. You can plug in this set down here, or this set up here. Okay, I'm going to go with these numbers. So essentially, in place of dg, I'm going to put x, or 1x basically, and then over 3x in place of gf. Okay, and you can cross multiply if you want, but all I'm looking for is if both sides are equal to each other. So let's go ahead and simplify this. I kind of already simplified this before. If you have an x on the top and an x on the bottom in the numerator and denominator, all like terms, like 4 divided by 4, they will end up canceling out because their greatest common factor is indeed themselves. The greatest common factor between 4 and 4 is 4. So they would simplify down to 1 and 1. Well, it's the same case with letters. X and X, since they're similar in the numerator and denominator, will cancel out, leaving you with 1 over 1. And then you know that the greatest common factor in 3 and 9 is 3. So if you divided by 3 divided by 3 into 3, that'd be 1. And then 9 divided by 3 would be 3. You have the same exact ratio. And if they are the same, that means that the ratios of EH to HF is equal to DG over GF. They are the same ratio, and they are proportional to each other. So that means by this theorem, the converse of triangle proportionality theorem, it says that in our case, DE must be parallel to GF. Okay. GH. I'm sorry. There we are. Okay. If you guys want, you guys can try. Well, actually, there's no solution key to this, so let's not. But you can take a look at this, or hopefully, what I gave you should help you with the rest of the questions on your homework like this. And also, what I'm not going to go over is the triangle mid-segment theorem. It's actually pretty close to kind of what we were talking about, but I'm not going to really focus on this. I think this is a little bit too specific in terms of information that I want you to really retain by the end of this course. But go ahead and work on these problems. I still want you to be exposed to it, but it's definitely not something that's going to be as intuitive to remember. I think this is a very, very narrow focus here. I think what you should focus on, and what we're going to go over next, is this: corollaries 9.1 and corollary 9.2. This is what we're going to go over in the next part, and I will see you then. Okay, guys, you guys have a great night.